All right, we're going to get back to chapter 2, part 2, and we're going to look at Newton's first law of motion. Now, Newton's first law of motion is going to sound pretty familiar because basically he just took what Galileo already said and reset it. So then we're going to talk about net force and the equilibrium rule and support force, the equilibrium of moving things, and the moving earth. Okay, so Isaac Newton, what a guy. Now, he lived from 1642 to 1727, and if the number 1642 sounds familiar, well, that's because it was the year that Galileo died. So Newton was born just a few months before Galileo's death. And Newton was in England, but his was a time that was much freer. He was born during the Reformation, and being in England, where the king had rebelled against the Catholic Church and started its own church, then he didn't have to worry so much about Aristotle's words. Anyway, so he picked up basically where Galileo left off. He was brilliant. He invented calculus and the reflecting telescope. I also put on here the cat door to add a little humanity to the man. He liked cats, and he is the first person recorded in history as creating a separate door for cats. He did research in motion, light, and gravity. And so he wrote a book called the Principia, The Principles of Natural Science, and a book on optics that are the standard basis for a great deal of physics. Anyway, he has more laws than anybody else, so we're going to be studying his 3 laws of motion and his law of gravity as we go along. So, and some other laws of his. So, law of heating. Anyway, Newton was just amazing. Okay, so let's keep going. Now, Newton's first law of motion, as I said, will sound familiar. It says every object continues in its state of rest or in uniform motion in a straight line. And uniform motion, what we mean there is constant speed. Okay, uniform motion means moving at a constant speed. And so unless it is compelled to change that state by forces impressed upon it. So an object that's sitting still will continue to sit still. An object that's moving will continue to move unless forces change it. So this is exactly what Galileo was talking about. And so this became the first law of motion for Newton. And then he built the second law and the third law on top of that. Okay, and they all tie together beautifully. So it's okay that he used Galileo's ideas to write the first 3 laws. Now, Newton did acknowledge that he got a lot of benefit from the people who had gone before him. So there's a famous statement of his that he says, "If I am great, it's because I have stood on the shoulders of giants." So Galileo was one of the giants that he stood on, and Copernicus. Okay. So anyway, so this law has a nickname. They all have nicknames. This one's called the law of inertia. Because remember, we're talking about objects that naturally have inertia. And if you want to change motion, then you have to apply forces. And we'll talk about what's called a net force later. Okay, so anyway, so here's a big rock. It's in Yellowstone Park. It's going to stay there until forces come along to change that. And in fact, this giant rock was probably carried there by a glacier. So it has been moved before. And here's a spacecraft out in space, and it's going to keep going because there are no forces to stop it. And so it might go into orbit around a planet, If it's aimed to do that, or if it's aimed in between the planets, it may just keep going straight for a very long time. So right now, as I said, there are spacecraft that have been traveling for around 50 years, and they have reached what's called the edge of our solar system, which is considered to be about 100 astronomical units. An astronomical unit is the distance between the sun and the Earth. And so these spacecraft are now 100 times as far away. And if you're wondering, is that beyond Pluto? Yeah, Pluto's at around 40 astronomical units. So Pluto is at around 40. Okay, so they are way out there. Now, inertia is all around us all the time. When you flip a coin in a car or you toss something in a car, it behaves as you expect it to behave, right? It doesn't go flying to the back of the car usually, unless you're hitting the brakes, in which case you've got other issues going on, other forces. But the thing is, inertia is the idea that when you are in an airplane and you toss something up in the air, it should return to your hand the same way as if you were sitting still on Earth, even though you're traveling at 500 miles per hour. Now, why is this? This was actually something that people had trouble with. The idea that the Earth was moving, which we'll talk about, but the fact that you can move and everything would still act as normal. And the reason for that is when that coin was in your pocket, okay, and the plane used forces to accelerate you because your seat is tied to the plane and the plane has engines. And so there were forces that were accelerating you up to 500 miles per hour. Well, it wasn't just your body going at 500 miles per hour, but also the coin in your pocket was going at 500 miles per hour. And when you take it out of your pocket and you flipped it up in the air, it is still going sideways at 500 miles per hour, or forward at 500 miles per hour. So it keeps up with the plane. It doesn't fall behind the plane. It hasn't lost that speed because it has inertia. And to change its motion, it would have to receive a force that was directly going to oppose that motion. And it doesn't. It's just taken out of your pocket and tossed up in the air, and it's still going 500 miles per hour. Now, if you tried to do this when the plane was speeding up, well, then your coin would be going 500 miles per hour, but maybe you would be going now 550. Well, what would happen then? Then the coin would fall behind you because you would have gone forward under the coin. You were going faster. And the same thing, what if the plane starts to slow? Well, then the coin might still be going 500, but now maybe you're going 450. And so the coin would fall ahead. Okay, so anyways, this is something you could try, two drivers. You could be tossing a ball in a car and see what happens when there's a braking or when you're accelerating. What happens to the ball? Okay, but if you're moving at a constant speed, then you should be able to toss a ball back and forth as normal, as you normally do in a car, obviously. All right, we used to toss my baby in the airplane. When he was young, my son was restless in an airplane, of course, but he liked to be tossed. So I'm sure the people behind us were amused to see this baby going up and down, up and down. He did not fall to the back of the plane. Okay, and this was one of the problems, as I said, that people had with a moving Earth. If the Earth was moving so fast that it could circle the sun in 1 year, then that's an incredible speed. And in fact, our Earth is moving at 67,000 miles per hour. Hugely fast. So people were saying, well, that's impossible, because then if a bird tried to fly, it would just get left behind, right? So the thing is, the bird could sit on the tree, that's fine, but when it flew, then that's ridiculous. It can't fly at 67,000 miles per hour. But the thing is that the bird was born going 67,000 miles per hour, just like the tree, and it has that velocity. So any little bit of velocity it has going up, down, left, right, as it flies around is just adding to that natural motion of 67,000 miles per hour that it doesn't have to flap its wings, because it just has inertia. And because it has inertia, then it retains that motion its whole life. So we don't feel the movement of the Earth. And there's only a few things that give an indication that the Earth is moving besides the visual evidence. But one thing is that the weather system is what's called the Coriolis force that causes weather to go into cyclones and things like that. That is actually part of the fact that we have a moving Earth. Can't explain it with a non-moving Earth. Okay, let's talk about net force. So net forces are when you're adding forces up. So what we've got here is on the left side of this column, we've got the applied forces. And on the right side, we have the net force. Okay, so we have a block, and the first block has two 5-Newton forces. And remember that the unit of force, which we talked about in the metric system review, the unit of force is the Newton. So, and that is about 2.2 pounds. So each Newton is 2.2 pounds. So 5 newtons would be over 10 pounds of force. So we're pulling on this block with 5 newtons of force. And then there's another 5 Newton force. Well, together they would equal 10 newtons. Okay, so these are what are called vector forces. Vectors have arrows, vectors have a direction, and because they have arrows and a direction, they can be added up. But they can also add in opposite directions. So here we've got a 5 Newton force to the right and a 5 Newton force to the left on the second block. So what happens? Well, you can think of one as positive. Usually we think of things to the right as positive, just like a number line. Right is positive, left is negative. And so we can think of this force as a negative force pulling in the opposite direction. And so together, 5 minus 5 equals 0. And finally, we've got our final example here. We've got a block that has 10 newtons to the right, 5 newtons to the left. What's the answer? Positive 10, negative 5. We end up with plus 5 to the right. Okay, so that's the idea of net force. We're just adding up the forces. Okay. All right, so let's look at this, because sometimes you've got more than one force, right? You can have several forces, so let's just do a simple example. So here we've got a block. Oops, really bad block. Okay, and we're going to pull on it with some forces. And so let's make it 10 newtons this direction. And then we've got 2 newtons. And then we've got an additional 4 newtons. Okay, so how would you add it up, right? Well, you can add it up like an equation. This is going to be positive, negative, negative. So you're going to have 10 newtons minus 2 newtons minus 4 newtons. And of course, that just leaves you with 4 newtons of force. And that's what we would call the net force. And the net force, you're just adding up the forces. So the net force is equal to force 1 plus force 2 plus force 3. Now, let's say that we change this a little bit, And we make this force minus 12 newtons. Okay, and now what do we got? Now we've got an imbalance the other direction. Now we've got minus 12. 10 minus 12 minus 4 means that we've got minus 6 newtons. And in physics, the minus sign doesn't mean bad. It doesn't mean the thing is experiencing anything unusual. Minus signs usually just mean other direction. So the net force is now minus 6 newtons to the left, or 6 newtons to the left. And so that's what the net force is going to be. And we can write net force as F of n. And well, I'll show you another way in a minute. Okay, all right, so it's very simple, just adding up the forces. And in this class, we're not using trig, so we're not going to have forces off at angles usually, and all that fun trig stuff. So if you took a class already that has that more fun trig aspect, that's not going to happen here. Mostly our forces are in a straight line along one axis. Okay, now in your book, there's the scaffold story, which is the story of the author, and how when he was a young painter or window washer, painter, I guess, he was wondering, well, what about the tensions on the ropes? And he was wondering, well, what happens if I walk across to the further rope? Is that going to place more tension on it? So tension is the force of hanging objects, the pulling force. And so he was wondering, well, could a rope break if I walk over there? So that was one of the reasons that encouraged him to continue in physics, is his summer job. So you might want to read the story. Okay. And by the way, he's the one who draws all these pictures. So he's the artist. Okay, so tension is the upward pulling force, which can balance out a downward pulling force. So here we have some sugar, which is 2 pounds of sugar, it says. Okay, so there's 2 pounds of downward force. And so the string is providing 2 pounds of upward force. And that's about 9 newtons. So every kilogram is 2.2 pounds, which is about, so that's about every 10 newtons is 2 pounds. Okay, 2.2 pounds. Okay, so I think I said earlier that each newton was 2.2 pounds. It's each kilogram. Okay, all right. So, so tension is the upward or the pulling force. And so, yes, he was wondering what happens to the tension as someone walks across. And so here, in this picture, you can see that this rope over here is gone slack. So actually, there's no tension here, right? Because it's no longer pulling on the board. So that means that the weight of the board, the scaffold, and the people and the paint buckets, all that is the tension here, right? So there's no tension on the right. Okay, now, the rope didn't break in that case. And the idea is that when the net force on an object is 0, the object is in mechanical equilibrium. Like the sugar packet here, you want the upward force to balance the downward force for hanging objects. Then it would be in what's called equilibrium. Equilibrium will not change its motion, and that's basically what you want when you're balanced on a scaffold or when you're trying to pick something up or hold something. Still, you don't want it to be moving. So it has to be in mechanical equilibrium. And mechanical just is referring to the fact that it's not electrical or something like that. It doesn't have anything to do with light. It has to do with mechanics, which is the field of physics, which covers motion and movement of objects and mechanical devices. Okay, so no electricity. So anyway, so equilibrium is just that idea of balanced, right? Something is in equilibrium, it's balanced. And the object does not change its motion. And we can use some symbols for this symbol, if you've come across it, probably you have in math, means sum of. And so that's another way to write net force. Net force can be written as sum of forces, which some of us like to do. It's easy to write, easier than writing net force. Don't forget you can write F of N. Okay. Okay. And so then that would just be a sum of forces. So again, that's adding up the forces, however many there are. And in this case, when it's in equilibrium, that net force should come out to 0. So we already saw that in the blocks earlier, the middle set, the force to the left and the force to the right balanced, and so we got a net force of 0. So if we have a block and it's being pulled by forces, okay, so the force to the right, if that was 12 newtons, then for it to be in equilibrium, the force on the left would also be 12 newtons. Okay, so it's in equilibrium. Are those the only forces on the block? Probably not, because there's probably gravity, but we'll talk about that in the next chapter, or actually coming up soon. Okay, so anyway, so when you're on a scaffold, you want the net force to be equal to 0. And so your gravitational forces, in this case, the weights of the objects, must be balanced by the tensions upwards. Okay, so you've got a couple of homework problems like this. So let's do one. And the idea is we want the net force to equal 0, but we've got one force that's going to be your unknown. That's how your homework problems work. So we've got, let's say we've got some weight on these people. Remember that people usually have a mass of about 50 kilograms. So that makes their weight about 500 newtons. And so we're going to have this guy be about 500 newtons. And the other one is a little heavier, so let's make him 800 newtons. And then the board itself is kind of like the weight of a child or something. Let's make it 200 newtons. Okay, and let's say that the forces on the left side, this tension, is going to be 900 newtons. And what we want to do is find out tension 2. Okay, so how do we do that? Well, we set it up as an equation is one of the ways. There are two ways to do this. One way to do it is probably sort of what you might do by instinct. You might say, okay, my downward forces and my upward forces have to be equal to each other. So you might say, okay, these are the downward forces. These are the upward forces. And my net downward force is going to be 1,500 newtons. So that has to be what my net upward force is. And you can probably look at it and say, okay, well, I got 1,500 newtons downwards. And that's going to equal 900 newtons plus the second tension. And so your brain has probably already figured out that that means that T2 is 600 newtons. Okay, now that's one way to do it. And that's your brain doing some of the steps that you could more formally do, like I'm going to show you with a formal equation where you start out saying net force or sum of forces equals 0. And the thing is, you just list all the forces, right? Because you're just going to add up all the forces, etc., right? So in this case, we're going to have the upward force of 900 newtons plus T2. And then we're going to subtract the others because basically they're in the opposite direction. Usually we think of up as positive and down as negative. We're going to add negative signs to them. Okay, so then that's going to be minus 800, minus 200, minus 500. And I know that this whole thing has to equal 0, right? Okay, so you would just do this as a math problem. You would add up the real numbers on the right side. 900 minus 800 minus 200 minus 500 becomes 600. Sorry, minus 600. And that equals 0. So then you would put your T2 on the other side or your 600 on the other side and end up that T2 equals 600. Okay, so T2 equals 600, and don't forget the unit, newtons. Okay, so anyway, so that's the way you can do it in your book. You can sort of explain it using the up-down idea, or you can do it as a formal equation, but you should show your work, even if you're able to just figure it out using your massive brain. Okay, like Aristotle. Okay, but let's have some proof in here too. Okay, and to answer that question, he was worried about how that would change tensions as someone walks across the scaffold. And yes, it would. And because the net force has to remain 0, then as you walk across to the left rope gains forces. So the right rope would lose that much force. Okay, so the tension would get less on the right, greater on the left. Okay, now there are other forces on objects that have to do with gravity, but there's also one that Newton figured out called the support force. Because equilibrium is required for something sitting still, well, when you look around you, probably a lot of things are sitting still in your room if we ignore the fact that we're sailing through the air at a huge amount of speed. So anyway, through space. Anyway, but what we've got here is a book sitting on a table. And why doesn't it just sink through the table? Gravity's pulling on it. And of course, you're thinking, well, because the table's in the way, right? But what actually is in the way? The table has atoms, right? And so there are atoms in the table. And the thing is that those atoms are kind of in the way, but atoms are actually like 99% empty space. So really, the atoms in the book and the atoms on the table should just slide through each other because there's so much empty space. But obviously they don't. What happens is that the electrons going around the atoms, those are negative. And they repel the atoms that are in the book, which also have negative electrons. So what you end up with is an electrostatic repulsion from the electrons. And so right now, as you're sitting in your chair, if you're sitting in your chair, your bottom is repelling your pants, and those pants are repelling the chair, and the chair is repelled by the floor. And so because of that, everything is in equilibrium, so you can sit still. And if you get up and take a step, you're balancing on the electrons in the floor. And every step you take, the electrons are repelling. And so when you place the book on the table, it starts to sort of sink in like you do when you sit on a couch. You sink down until the coils in the spring push back upwards. But the same sort of thing is happening with the book. It sinks down sort of into the table until the electrons repel enough. It's not enough for us to see with our eyes, but yeah. That's what's going on. Electron repulsion. Okay, so this provides a force, which we call the support force. And so when two surfaces are in contact with each other, there is this force that comes out of that. So it's also called the surface force. And it has a third name, which is the normal force. And it's called normal, not because it's normal to have one, but because normal means perpendicular for scientists. And this force is perpendicular to the surface. So it's at 90 degrees. And so anyway, that's why it's called normal force. So often we'll call it the normal force. Anyway, in this case, the book is resting. It's at rest. It's still. And so the support force is equal to the gravitational force. So let's say the book had a gravitational force of 10 newtons on it. Well, since it's at rest, we know that the normal force is also 10 newtons. And if you want, you can make this one negative. But the idea is the amount is 10 newtons. The direction is the negative. It's not a lack of 10 newtons. Negative just means other direction. So anyway, so this book is in equilibrium. So anything you see sitting still, anything at rest is in equilibrium. But we're going to talk about that some moving things can be in equilibrium too. So static equilibrium is when an object is actually at rest in respect to the planet, because obviously our planet is moving. We're just not going to count that. Okay, so static equilibrium, the object is at rest. And so here's this guy, and he's like, oh no, I weigh 900 newtons. Well, that's because the springs in the scale are pushing back upwards with a force of 900 newtons, right? So the support force is 900 newtons, and that's what you're reading on the scale. Oh, other way around. Had it right, and then I changed it there. Okay. Okay, now, so here we have, first we have Charlie here. Just call him Charlie. And let's say that Charlie weighs only 500 newtons. First of all, he's standing on two scales, and he is therefore, and he's standing equally on both of them. So his 500 newtons is downward. And that's going to be, of course, opposed by the support force. And so each scale is going to do part of the work. Okay, 250 newtons each. And also, because we can draw this with arrows, usually we would draw the 500 one twice as large, okay, which makes him look like he's drooling there. Okay, but sometimes it's hard to do with this pencil. Okay, anyway, so here we've got Charlie standing on the scales, but now he's got more weight on one leg. So let's say that this scale is reading 300 newtons. Okay, so then you know that the other scale must be providing the other 200, because we still need a net force of 0. So we still need to balance out that 500 newtons. So equilibrium is not just for things sitting still, but also for things moving. If they are moving at a constant speed, so that's critical, in a straight line, then they also can be counted as being in equilibrium. The net forces are still 0. And this is called dynamic equilibrium. Dynamo means movement. Okay, so dynamic equilibrium. And in this case, it's still in equilibrium, so the net force is still 0. It's just the object is already moving. Now, this would happen if you started a ball rolling. Okay, if you start it rolling or throw it, you will have to apply a force, an unbalanced force. But then once it's going and it's rolling along the tabletop at a constant speed, then you can say that the net forces would be zero on it. It's moving at a constant speed. Okay, so this is what happens, when you're shopping in the grocery store. You're pushing on a cart, and so you're pushing on it, but you're not constantly speeding up and slowing down. You're trying to move at kind of a constant speed. And so you've got a pushing force balancing a frictional force due to the cart wheels on the surface and the bearings in the cart. And so they just balance each other out so that it moves at a constant speed. So be careful in your homework problems. If they talk about something moving at a constant speed, you instantly know that you're talking about equilibrium. And so the net force should be zero, even though you're always tempted, because something is moving, to make one of the forces bigger. But it's when you're driving your car. You're like this airplane. You drive at a constant speed often. So you're trying to maintain the speed limit, 25 miles per hour. It's hard. But what you're trying to balance there is the thrust of your car, the engine pushing forward. And then you've got the air friction and the friction from the road in the opposite direction, okay? Trying to keep you from going. So that is what was recognized, was that you would have a balance of forces. So next time you're driving your car, notice what happens. You always have to keep the gas on, usually, to go in a straight line on a flat surface. And that's because you are just balancing out the frictional force. So here we've got Nellie, I think the author calls her, pushing on a box with 75 newtons of force, and there is a negative or backwards force of 75 newtons. Okay, as long as the box isn't moving at a constant speed, those two forces are equal to each other. Now, Nellie probably had to push a little harder to get started. We'll talk about that in another chapter. But once it's started, she can just keep pushing with the same force. Okay, and that's the end of this chapter. And so we will pick up chapter 3 soon. All right, so that's the end of chapter 2. Oh, there is one project you might want to play around with. There are these projects in your books that you can do, these at-home things, and you can write those up for extra credit. Don't hurt yourself doing them, but what you do is just explain what you did, and usually 20 projects is worth 10 points extra credit. So that's something. Anyway, but anyway, you don't even have to explain the physics necessarily, just explain what happened. But one of the fun ones to do is where you place books on your head and then have someone try to nail a nail into a block of wood. Okay. Now, normally you'd expect this to hurt, but the idea is that these books, they've got so much inertia that hitting them with the hammer doesn't add a whole lot of extra force to the top of your head. And because they have inertia, then they have resistance to change in motion. So they don't press down harder on your head. So anyway, so you might try it with someone who you can trust and see what happens. Okay, and without the books there, of course, it is going to hurt. Okay, see you later.